And this is our fabrication facility, or at least a part of our fabrication facility in Fremont, California, where we actually fabricate the chips that we design. That's what a wafer looks like. So that contains 8 actual chips. The chips are a little bit smaller than the size of your pinky nail, so you actually can see the qubits on them. They're macroscopic. And that's an 8-qubit system, so you can see the 8 squares around each of those. So we've just announced our new flagship product, Quantum Cloud Services, which is a cloud access point to our quantum computers. We've had quantum computers available that you can run on over the internet for a little over a year now, and now we're offering a much more HPC type access point to our quantum computers. So another fun animation of kind of what that looks like. We offer an access point that is effectively similar, like I said before, to an HPC access point, and we've built in a bunch of fun resources that I can talk about when I have more time later. So also, I threw this slide in for the folks in the room who are interested in doing business development. We have announced a Quantum Advantage Prize, which is a $1 million prize given to anyone who can use a quantum computer to demonstrate what we call quantum advantage. So you'll hear terms like quantum advantage and quantum supremacy thrown around a little bit. Quantum advantage is the point at which you can use a quantum computer to solve a problem better by giving a better solution or better approximation to the solution faster or cheaper than you would spend on an HPC type resource. So that's it. And with that, I'm happy to take any questions.
So I applied for your beta access a while ago, right? Have you heard anything? Is there a fast track?
Yeah, so you and Isaac and probably a bunch of other people in the room have been waiting for beta access with our first 16-qubit processor. Isaac actually will be one of the first people who will be testing this platform. So with that said, if there are a lot of people on our wait list, we have had thousands of people get onto our wait list. So put up my email before I can talk to you after too, but if you're interested in getting up a little bit, you should reach out to me.
What's the most advanced quantum advantage computing you have achieved so far?
Oh, we haven't achieved quantum advantage. I think, like Stefan said, I think quantum advantage is something that we expect to be at least a couple years away. It requires a really robust and powerful quantum computing resource.
So what kind of application will be achieved first?
Oh, I think we're going to get into that in the panel, but I think there's anything, it's a powerful resource for solving really hard problems. So you can expect that maybe it's interesting for combinatorial optimization problems or anything to simulating other quantum mechanical systems.
Right, I think the question, do you want better first, faster first?
Oh,
Could you repeat his question?
yeah, okay, so the question was, when we talked about advantage, we said better, faster, or cheaper. My expectation is it will probably be, we'll expect better first. There are some problems in condensed matter physics that we think we can give better solutions to. There are certain, for our chemists in the room, there are certain variational algorithms you can run on our platform that give you a unitary coupled cluster level approximation of an electronic structure.
Since you're a fabrication company, can you speak of the equivalent of Moore's law, where the improvement in hardware can drive the scaling of the performance of quantum computing?
Yeah, so I think we'll hit that at some point. Oh, sorry about that. Yeah, so the question was, is there a Moore's law equivalent that we'll see with quantum computers? I think there's probably two. I think the first threshold is the one that's most proximate, which is this chasm between kind of these noisy quantum computers that are very small in scale that we have currently, moving to large fault-tolerant systems that are going to be able to solve really hard problems like the perennial Shor's algorithm and stuff like that. And then, after that, you'll see probably some Moore's law type scaling.
Last question.
So when you were talking about fab, you use the word commercial. Does that mean you're selling out fab services?
No.
It's not really commercial.
Not yet. Maybe one day, but no, not yet. Cool. Thank you.
Okay,
more efficiently with quantum computing resources. And those things include, a prime factorization algorithm called Shor's algorithm, which can help to break crypto. Quantum chemistry, which is simulation, optimization, and so forth. And that medium blue center circle certainly isn't drawn to scale. So really the range of problems that can be solved with quantum computing, with the quantum computing algorithms that have been invented to date, that have provable end-to-end speed up, is really quite small. And then that green area within that medium blue thing, that's the problem type that can be solved by not these universal quantum computers that are being built by Rigetti, IBM, and Google, but rather there's one commercial project, well, 1.5 maybe, but one that doesn't use gate model quantum computing to solve problems, but rather another protocol called quantum annealing to solve problems, and that's D-Wave. D-Wave's kind of well known because they've been around so long, and they were kind of a pioneer in building these processors based on a more rudimentary kind of processor technology. Anyway, we work with both gate model and annealing quantum computers. And to put very simply, the best quantum computers today that are exposed, you can still solve larger problems faster on a MacBook Air than you can on a quantum computer, but that doesn't daunt everyone in the technology community that cares about this resource. They understand that in the course of time, quantum processors will become more powerful, and at some point they'll intercept the power you've got for certain problems in classical compute resources. But generally for our company, we look at the types of problems enterprises have that can be addressed with quantum computing resources, so algorithms and hardware, and this is kind of the range of them. So what our company actually does, we generate revenues, and the revenues we generate are not product revenues necessarily, but we do application prototyping for Fortune 100 companies, Fortune 200 companies, companies that have long product life cycles and have R&D budgets, because that's really what these projects are for companies. So as one or two of the panelists mentioned, none of this hardware is ready for prime time, but there are early adopters in the enterprise community, some of them in the Valley now, that are taking small calculated bets on working on developing applications in-house with the help of companies like ours to figure out, hey, here's a problem we have, it's a computing bottleneck. How can we possibly shorten the compute time of this problem by running it on a quantum computer? So what we do is develop so-called quantum representations or mappings of that enterprise problem into a formulation that's runnable or executable on a quantum algorithm on quantum computing hardware. And we're fortunate to have partnerships with Rigetti, for instance, where we do some of this prototyping and some of the other hardware.
You know, light is traveling past itself all the time through the room right now, and it doesn't care. This allows us to do a bunch of things that you can't do when you're sort of fully constrained into 2 dimensions. But the number one reason that we're following this approach is it's none of those sort of quantum advantages of light. It's this classical advantage that the approach that we're using is fully CMOS compatible, which means that I can do it in a standard silicon foundry. And so we say it's manufacturable. It's not just a question of theoretical scalability, it's that we can really build, the millions or in fact trillions of components in your laptop. We use the same foundries to try and build 1 million qubits. Now light does have disadvantages, and the number one disadvantage is that the photons do pass through each other. They don't like to interact with each other. And so you have to use some tricks of interference. You've probably all heard of like double slit interference. We do some variation of interference like that to create entanglement between the photons. Okay, so what is PsiQuantum? Well, PsiQuantum is based here in Palo Alto. That's our headquarters. We have the symbol Psi pretty much everywhere. It's out the front, it's on the glass door, it's on our jacket. I have some Psi earrings, like it's Psi is kind of everywhere. And if you ever come into the building, this is what you're going to see. We have a bunch of engineers and a bunch of architects. And the architects sit around thinking about how to design the thing and lay it all out. And the engineers sit in front of some computers And essentially what they're doing is they're producing CAD diagrams like this. So this is the standard file format, it's called GDS file, that is the same thing is used when someone builds your laptop. It's basically, I mean, this looks 2D, but it's really a fully 3D thing that says, here, layer by layer, here's what a silicon fab foundry should lay down, the type of material, what it should etch away, and so on. So we produce these kind of diagrams, we sit down on the computer and do that. If you zoom in, so this is one of our early diagrams. You can see that this particular one, there's actually thousands of components. Like, I could zoom in even more, and you can fly around, but there's tens of thousands of components. In fact, all sorts of different ways of laying them out. And this file, it's a bit like fancy 3D printing. You design it, you sort of work it all out, and then you hit print, which basically means that you email it or upload it to the foundry. And then they normally come back. It's not quite as simple as standard 3D printing. They normally come back and say, oh, there's some problems. And so you have a bit of a back and forth, but eventually they accept it. And so we just send it to a top of the line 300 mil fab. Okay. So the fabrication tools that we insist that our engineers use, we do not design or use any components that cannot be built on the very best silicon fab foundries in the world today. And in fact, we test these foundries, we work with them to help them understand and improve their processes. But essentially we send these things off, and they, after a few months, send us back a pizza box that contains a full wafer like this. So this is a few years old, but this was the first 300 mil wafer ever produced on a top-end CMOS line with tens of thousands, in fact hundreds of thousands of photonic components on it. Okay. And that device, if you say, what's really going on in there? Here is a standard quantum optics lab. If you ever walk into a university academic quantum optics lab, you'll see, hundreds or a few thousands of components. This would be something like a sort of 8-qubit photonic state experiment. On this wafer, we have, the equivalent of tens of thousands of that laboratory, of that whole academic lab, can fit on this one wafer. The other thing that we can avoid by going to this process is, you see those creatures there, they're called PhD students. Those of you not in academia don't know that they're an extremely problematic piece of lab equipment. They smell, they put fingerprints on things, they're really kind of annoying. So because everything we're doing is built around the standard silicon industry, we replace the PhD students with essentially a robot. And we use a standard robot that can go through, put the light and so on, do all of the measurement characterization and so on of all the different components, and then sort of upload the data into a database, goes back to the monkey sitting in HQ. Okay. Now, if you ask, what are those components that we're building our qubits from? They're actually fairly standard silicon photonic components. So if you look here, the waveguides that we make, which sort of capture the photons that they're propagated on, are actually very big. Like, if you come from the silicon industry, you're used to kind of extremely small components. You might say, why are we using a top-of-the-line fab? The reason is that the tool set that they have, they've invested $100 billion improving that tool set so they can make everything extremely precise, repeatable, and smooth. We gained a huge amount as soon as we started using these processes. But the structures that we make are big. Some of them you can almost see with your naked eye. You can see some of the delay lines, which we made extremely big just because those are sort of world record low loss delay lines. It's extremely difficult to measure the loss. So we had to make them very big and then stick a photon in and let it spiral around until we lost it. But the structures are quite big. They're sort of hundreds of nanometers. You see that we have rings, we build detectors, which are just a piece of superconducting material sitting on top of the waveguide. We have the delay lines, we have filters because we're putting lasers down into this thing. We've got to filter the laser light out extremely strongly. We have switches, we have couplers. But every single one of those components is something that was already built in silicon photonics for classical reasons. And the two main classical reasons are self-driving cars. LiDAR is also built from the same kind of processors. And the other are the optical internet connects and data centers. So this is the sort of Intel perspective on how they want to use these silicon photonics for using, for replacing sort of electrical circuits by line circuits.